Oh, it's a very exciting time.
Where's the universe made out of antimatter?
We are looking for unusual phenomena.
And we call it astroparticle physics.
We're really excited about this upcoming mission.
Hello, good evening and welcome to CERN. We're here tonight to discuss the science of the Alpha Magnetic Spectrometer, AMS, a particle detector that makes up the payload of the Space Shuttle Endeavour for its last ever mission into space. That was scheduled to begin today but has now been postponed until at least Monday. AMS was assembled here at CERN by an international team of scientists led by the Nobel laureate Sam Ting, and when it reaches the International Space Station it will be addressing some very fundamental questions about the universe we live in. Tonight we're joined by some guests to tell us all about it. Sylvie Rosier is a scientist working on the AMS experiment. Thanks for being with us tonight. Michael Dozer is a CERN physicist and antimatter expert. Good evening, Michael. Good evening. Arnaud Marsollier is head of communication at IN2P3, the French member of the AMS experiment, and he is following the hashtag AMS02 on Twitter. So if you have any burning questions you'd like to know about the AMS experiment, send us a tweet and we'll do our best to answer you. Good evening, Arnaud.
Good evening.
And last but not least, Sergio Bertolucci is CERN's Director for Research and Scientific Computing. Welcome, Sergio.
Good evening, everybody.
Later in the evening, we'll also be joining my colleague, Paola Catapano, live from Florida. But first, let's find out from NASA why Endeavour is staying on the ground today. Here's what they broadcast earlier.
This is Shuttle Launch Control. Joining us now in Fire Room 4 at our Public Affairs Console is our Space Shuttle Launch Director, Mike Leinbach. And Mike, I think we're looking at you to kind of explain how this problem evolved, what it is that you are seeing, and maybe give us some idea what the go-forward plan is and how much time are we going to need to turn around.
Okay, I'll be glad to do that. And can you hear me okay? I wasn't hearing you all that well, but well, let's see, the issues with one of our auxiliary power units, which provides the power to the hydraulic system for the orbiter. And the exact problem was a thermostat on one of the fuel lines for that auxiliary power unit, and we need to keep those lines warm to prevent them from freezing on orbit. So we have two thermostats, two heaters for each fuel line for each APU. And on auxiliary power unit number one of those two heater units failed, and the troubleshooting we did on it proved that it was a hard failure. We were not able to get it to come to life no matter what we did. We tried to let the line cool down just by normal means and to see if the thermostat on that heater would kick in. That did not happen. We tried to command the heater from the cockpit of the orbiter. That did not happen either. So we know we have a hard failure in that heater string for that one auxiliary power unit. There was another heater upstream of that is also exhibiting some funny behavior. So what we believe we have now is a problem in one of our LCAs, a load control assembly. It's essentially a switch box that says we probably have a failure, a short, actually in that box or in one of the electrical lines to that box or from that box. We're not quite sure yet. We won't know until we get into the after the orbiter and do some detailed troubleshooting. But the issue is that we didn't want to commit to flight with only one of two heaters on those auxiliary power unit fuel line because of the chance that if you lost that one good one on orbit, then you run the very high risk of freezing the fuel in that line, and therefore the auxiliary power unit would not function, and therefore you wouldn't have full hydraulic power, which is a case you never want to get into for re-entry without hydraulic power coming from one of the three auxiliary power units. So the course of action today is to scrub. We're in the process of draining the external tank right now. That'll take another hour or so. We'll set up to gain entry into the aft compartment of the orbiter overnight tonight, and probably tomorrow afternoon we'll get into the aft, start putting in our platform set to get to this load control assembly, which is down inside the aft quite a ways, and so it's going to take us a bit of time to get in and do that. And then once we're in the avionics bay where that LCA exists, we'll be able to do our troubleshooting and see if we need to change out that box or whether we find a short in the line, that type of thing. So right now, it obviously a scrub turnaround scenario of a minimum of 72 hours right now. We've declared a minimum of 72. And I'm going to have a scrub turnaround meeting with my launch team at 2:30 today where we will refine that plan based on engineering's input to see what level of troubleshooting they want to do to see if it extends that 72 hours even longer than that. But today the orbiter is not ready to fly, and as we always say in this business, we will not fly before we're ready, and so that's the case we're in today.
So right now we're no less than 72 hours, but till you get through the troubleshooting in the aft, you really can't tell how much more time we would need.
That's exactly right. We're absolute minimum 3-day scrub turnaround now.
All right, Mike, well, thank you very much. And that will conclude our launch commentary at this time. This is Shuttle Launch Control.
So prudence there, carrying the day, it seems, at the Kennedy Space Center. But what nevertheless sound to be rather minor technical problems and eminently solvable. But for somebody who's been working, Sylvie, towards this day for 10 years, it must be a little disappointing.
A little bit disappointing, but it's a matter of two or 3 days. So we wait for so long time about this event. We are so close to the final goal. So I'm a little bit disappointed, but I'm still hopeful and confident for the future for our project.
Tell me, what sort of jobs do people have? What are the roles that people play on an experiment like AMS?
Basically, it's like usual particle physics detector jobs or roles that we have. We know AMS is a group of sub-detectors inherited from the high energy physics technology. So we have different kind of detector. So physicists are in charge of the design, the production, the performance measurement, and they have to test it also on different test bands and test facilities. So that's typically the role of the physicist.
And your role particularly?
My role, in fact, so I'm responsible of the French group of the AMS collaboration, and more as a physicist, I was in charge, with my colleague of my laboratory in Annecy at lab, of the construction of the calorimeter, electromagnetic calorimeter, the performance measurements, and all the analysis preparation linked to the electron, positrons, and gamma detections.
So now the shuttle's ready for launch, your job changes quite dramatically, I imagine.
Exactly, yeah.
Okay. There's an awful lot of good science to be done with the AMS detector, and we're going to go on now to a short film to present us with that science.
When it comes to understanding the universe, we are only beginning. Humankind continually searches for patterns, trying to figure out what is the universe made of? How does it work? How does our planet, our solar system, our galaxy fit in with the other pieces? And what don't we know yet? Helping us discover more pieces of the puzzle will be a new instrument on board the International Space Station called the Alpha Magnetic Spectrometer, or AMS. AMS is not a telescope. Rather than looking at space, it will sift through space, studying the high-energy particles of cosmic rays. From the unique vantage point of Earth orbit, the AMS experiment has the potential to answer questions about the origins of our universe. It began with a bang. The Big Bang Theory postulates that the universe was created in a great explosion. But there are some puzzle pieces missing regarding the Big Bang. During this explosion, matter and antimatter should have been created in equal amounts. But we have a hard time finding the antimatter in the universe. Where is it, and what exactly is the universe made of? We don't know for certain yet. Here's another missing piece. Astronomers have determined that galaxies have 10 times the mass than what we see of stars, gas, and dust. What accounts for this missing mass in galaxies? The answer may be dark matter, a mysterious material that exerts gravitational pull but does not absorb or emit light. But we have yet to find dark matter. The study of high-energy particles might help in the search for dark matter and antimatter in the universe. Nobel Prize-winning scientist Professor Samuel Ting, well known for groundbreaking particle physics work on Earth, has collaborated with an international team to create the Alpha Magnetic Spectrometer, a high-energy particle detector that takes particle science into space. He and his colleagues hope the AMS will help answer some of these nagging questions about the universe.
If the universe has come from a Big Bang, and so you have matter, you must have antimatter. Now the universe is close to 15 billion years old. The question is, where's the other half? Where's the universe made out of antimatter?
An alpha magnetic spectrometer flew on board the Space Shuttle in the 1990s, but that mission was only for a few days, merely proving the concept of flying this type of hardware in space. While valuable science was gleaned from that mission, the AMS on the station will stay for years, with instrumentation that is far more sensitive and far more precise than what was flown before, with over 300,000 data channels for detection and over 600 onboard microprocessors to analyze the data. The AMS is sponsored by the Department of Energy, and scientists from 16 countries lent their expertise to create it. Parts from around the world were sent to CERN, the European Organization for Nuclear Research, in Geneva, Switzerland. NASA had the job to figure out how to get the 15,000-pound experiment into Earth orbit and have it operate in the hostile environment of space. The AMS was finally sent to the Kennedy Space Center, where it was ready to fly on board a space shuttle, the final large component of the space station, to be sent on one of the last shuttle flights. Part of the shuttle crew is European Space Agency astronaut Roberto Vittori, who will operate the shuttle arm to grasp the AMS from the shuttle payload bay.
That means that I will have the responsibility with the shuttle robotic arm to take it from the payload bay and offer to the station. But behind that specific operational task, there is a very long history. I started about 25 years ago to study physics, to think about space, to think about the universe. And the specific of the search of the antimatter was one of my main and deep interests. It may appear
Okay, well, there are a lot of interesting ideas, a lot of fascinating images there, and we're going to have a chance to drill down a little bit deeper into all of those things as the evening progresses. But first of all, I'd like to talk a bit about the science of AMS. Sergio, what's the most exciting science that AMS is going to do?
In my opinion, dark matter is the hot topic there. Also because it comes very timely, because it will be nice just to attack this mystery from 2 points. From the point of the LHC and the point of AMS, of the space. And these two views are very complementary, and they might, at the end, just bring us to the next step in understanding about the physics, understanding about the fact that we are not understanding very much up to now about the universe, because apparently all the matter and the energy we know is only 4% of what is out there.
Which seems a very, very small number, and we'll come back to that later. And how about you, Michael, as somebody who's devoted their life's research to antimatter?
Well, my hope is, of course, that AMS will help us understand what happened to the antimatter that was present at the moment of the Big Bang, either by sifting through the cosmic rays that it will look at over time and detecting some antimatter particles or nuclei, or perhaps even detecting the products of antimatter stars or galaxies, which would be uniquely detectable by a detector that is as sensitive as AMS is. And this is something you can only do above the atmosphere. This is not possible here on Earth. So this is where AMS is unique.
Mm-hmm. And Sylvie, on AMS, do you have a preferred area of research, or?
Yes, I'm involved, in fact, in the dark matter searches. That it was said by Sergio. It's nice to see, to understand and to know the nature of the dark matter. So LHC will certainly tell us about the nature, field contents, and the mass of the dark matter candidates. But it's important also to probe it in space and to see how it is distributed. So that's really one of my dreams with AMS.
So dark matter and antimatter, the two key subjects for AMS. Arno, is there any activity out there in the Twitter sphere?
Yeah, there's much interest in AMS. Perhaps the first questions will be for Sylvie. People ask when you can expect big first results with AMS.
So big first result, I cannot say. I hope as soon as possible. But what I can tell you is that the first light, the first data will be taken 4 days after the launch. And I think during the few weeks, a couple of weeks of the two first months, we will already have a large amount of data and can explore new domains.
Okay, about data, there are technical discussions about how much data we can expect in a year, for instance, and how do you handle this data, how they come from the ISS to the Earth?
So we expect the total flux, I'm not completely sure, but it's almost 30 terabytes per year at the raw data level. Of course, if we reconstruct the data, the volume will be higher and bigger. But anyway, the data will be transferred from satellite to Earth, from the International Space Station, and then on Earth it will be first sent to in the Marshall Center of the NASA, because in fact data of AMS and ISS are multiplexed. So we have to, after that, on ground, separate AMS data from the ISS data. Then this data will be sent to the payload operating control center, the POC, and which will be in Houston, so in the Johnson Space Center for the first months, 2 or 3 months, and then after that, this POC center will migrate it to at CERN, where the data also will be analyzed and controlled.
Any more questions, Arno?
So perhaps a question more for Michael. People ask about antimatter. Can you describe what is antimatter, and could we imagine anti-me, someone asked?
So antimatter is very hard to describe because it looks just like normal matter. You can't tell by looking at it whether it's matter or antimatter, and this is what makes so hard distinguishing antimatter from matter in space, from identifying it out there. But the basic difference between matter and antimatter is that antimatter, it has the opposite charges of matter particles. For an electron, the antimatter equivalent is a positron, a positively charged electron. Every particle has their oppositely charged counterpart. If there were anti-worlds out there, anti-suns, it might be possible that there are more complex organisms made up of exactly the same type of chemistry, but made completely out of antimatter.
We're going to stay with the science now and go on to a series of clips about the science of AMS, starting off with antimatter.
It's long been known that particles such as electrons have a mirror twin with opposite charge. These inhabit the strange world of antimatter, loved of science fiction writers. In this case, the antimatter partner of an electron is a positron. In the presence of an electric field, they move in opposite directions. But CERN will be looking for an even stranger pairing. At the beginning of our universe, a minute blob of time and space, far smaller than an atom, began to expand, as a way of dissipating its extreme energy. Such three-dimensional spatial expansion that happens everywhere and all around us is well represented by this two-dimensional surface of a balloon that is stretching as it's been blown up. The Big Bang into pre-existing space is now seen as the big stretch of space itself. After a moment of extraordinarily fast expansion, the blob seems to have contained a plasma of particles. On further stretching, the quarks and gluons condensed into protons and antiprotons, which almost annihilated each other. But not quite. The few protons left over formed the basis of the universe we now live in.
Michael, let me come straight back to you now. My mind was certainly beginning to boggle already with talk of anti-worlds and anti-people and anti-whatever. I'd always thought that antimatter was something that had existed at the beginning of the universe and then disappeared. Is that not the case?
Well, certainly it must have existed at the beginning of the universe, and it must have existed in exactly the same quantities as normal matter. However, if that had been the case, there would have been no universe left over. Nothing would be inside the universe. So there must be some slight difference between matter and antimatter. This slight difference is one of the things that we hope to see, or else find out whether there is still antimatter out there. Now, you can also make antimatter in the lab to study it very precisely, such as being done here at CERN, by using accelerators, particle accelerators, to produce pairs of particles and antiparticles. This is also why we know that when energy transforms into particles, you always get a pair antiparticle with it, and which is why we believe that at the moment of the Big Bang, antimatter and matter must have been there in equal amounts.
So it's an either-or. Either nature has a preference somehow for matter over antimatter, or the antimatter is somewhere out there and we just haven't found it yet.
Exactly. This is the other alternative. If there is no symmetry breaking, if there's no difference between the two, then the antimatter must still be out there somewhere, just very far away from what we can see right now, at great, great distances, outside of the visible universe. On the other hand, AMS will tell us whether some of the antimatter is still around, some of the primordial antimatter is still in this universe.
And on the basis of current experiments and observations, is there one of these hypotheses more favored than the other?
Unfortunately, the experiments that have been done up to now, although they have extraordinary sensitivity, have not been able to find a significant difference between matter and antimatter. So we need to continue pursuing experiments in all possible areas.
So there may really be anti-worlds out there. Sylvie, why do we need to go into space to look for these things? Why can't we do the experiments here on Earth?
So as you know, we have plenty of cosmic rays impacting our atmosphere and then interacting. But as soon as they interact in the atmosphere, they are destroyed. So we lose all the information concerning their identity, their properties. So in order to measure their abundance, their flux, we need to go above the atmosphere in order to identify this cosmic ray. And that's the purpose of AMS. Because these cosmic rays are produced and accelerated in our galaxy at energy which are much higher than can be produced at the time being on Earth with even the LHC. So we have a lot of science to do and a lot of things to measure and to understand by measuring and identifying this cosmic ray.
And what would be the clinching signal that you'd found evidence for anti-stars or anti-worlds out there?
If first we discover any anti-nucleus of anti-helium or anti-carbon, I think it will be an important discovery and open new theory, new interpretation within this anti-star, yes.
Because there's no way they could come from anywhere but a star, is that the...
Exactly. We cannot produce antimatter, but the antiproton and positron, we know they can be produced through interaction of proton or helium within the interstellar medium, but we cannot produce anti-helium. So if we discover one anti-helium, it will mean that we have antimatter and primordial antimatter.
Fascinating stuff. And it brings us up nicely to our next clip, a short clip about cosmic rays.
Cosmic rays have been discovered about 100 years ago. It is particles that are produced by star explosion in its vast majority. then are somehow mysteriously accelerated and directed towards us. There's a lot of this radiation that comes on the Earth's surface. It's about several hundred per square meter per second. So it's not a small effect. It's a major ingredient to the environment of the Earth. It has something to do probably with genetic modifications. It has something to do with the climate. It has a lot of implications for us. And this means that we must absolutely know more about it than we do today.
Okay, so we're going to dip back into the Twitter sphere now before delving more into dark matter. Arno, what's happening out there?
Okay, so with what we said, there is a technical question about heavier particles. Could you imagine that it's possible to catch particles heavier than an anti-hydrogen or an anti-helium, for instance? And perhaps it's also a question for Michael.
Yes, it's possible. In fact, as soon as you are able with one instrument to measure for every nucleus the charge, the mass, the velocity, the momentum, so you can identify it. So the problem is we can detect it. The point after that, if we detect another kind of particle or heavier particle that we didn't produce on Earth, after that we have to interpret the things, but this is another question. First, we have to detect without any ambiguity. And that's the power of AMS, because it's the power of the measurement, precise measurement.
Michael?
I can just say the same thing, basically. You're not trying to catch the antimatter. You're just trying to detect them, to identify them very clearly. The detector has the possibility of identifying very clearly what the mass of the particle is and what its charge is. And so it's very well possible to detect, if there are any anti-carbon nuclei out there and they fly through AMS, to detect them uniquely without any background.
Okay, so perhaps another question, because we talk about how we catch particles and all this, but people ask how AMS will work. How is made a particle detector we send to space?
So AMS is a particle detector. Consists of few kind of type of detectors, and we have, for instance, we can measure, we can identify relativistic particle with one detector, which is the transition radiation detectors. So this detector is able to identify clearly positron or electron and reject, for instance, proton, because most of the cosmic ray which will be detected by AMS are in fact protons. They represent 90% of the cosmic rays. And if you want to look to measure and to look at a few particles which represent less than 1% of the total amount of the cosmic ray, you need to have a detector which is able to identify precisely this particle. So we have a TRD, but we have also the principle of AMS is a magnet. You have a magnet, and we want to measure or identify charged particles, which are the majority of cosmic ray. So to do this, we have a magnet, and then the trajectory will be deflected depending on the charge of the particle, and we have instrument inside the magnet in order to just measure the trajectory of the particle and measure the momentum. And this is made of the tracker detector, which is made of 9 layers from the top to the bottom of the detectors. And in the bottom of the detector, you have what's called the ridge, so ring imaging Cherenkov. And the principle of the detection is completely different. Here you want to measure also relativistic particle, but charged particle, and by measuring the emission of the photon Cherenkov. And by this way, you will measure the velocity of the particle.
It sounds like a very complicated instrument that you're sending up there, and probably a very delicate instrument too. The engineering challenges must have been quite significant as well as the scientific ones.
Completely right. If I can finish in fact, comparing to the collider detector for high energy physics, you know when the event will occur, the collision will occur. And then for all what concerns the trigger system, it's quite easy. Here we don't know because we have cosmic ray passing through the detector, and we have to decide very quickly if the event is good or not. And for that we have also another system which is a time of flight measurement, and which is able to measure the time with a very high precision at the level of 100 picoseconds. So and after that we have the calorimeter. And concerning what your question, it was in fact the challenge was twofold. First, we have to construct dedicated detectors with the technology of the high energy physics, which is already not so obvious, but we have to adapt this technology to space. And one of the most there were some different constraints from power consumption, so low power consumption. On ground, we are not limited by this constraint. We have also the weight constraint, so everything has been is computed with to minimize the weight of the total weight of the experiment. And last but not least is the access. So you cannot access to your detector, you cannot change, you cannot foresee any spare. So to do this, we have to foresee all the redundancy and all the failure possible. And to do this, we have, in fact, built 2 detectors for every subdetector and test all this redundancy.
So a very complex task just to get into space before you even start doing the science.
Yeah.
And let's get back to the science now. Earlier, Sergio, you were talking about the LHC and AMS and dark matter. We've learned that cosmic rays can tell us about antimatter. We've learned why it's important to be in space to look for antimatter. But what about dark matter? Do you have to be in space for that too?
Well, yes, because, antimatter, if antimatter is a good explanation of what we see, which might or might not be the case, because what we see is that in order just to think that the universe is rather flat, like is seen by many measurements, we have just to make a few assumptions. One of the assumptions is that laws of physics are equal almost everywhere, let's say everywhere. Gravity is working in the same way at every scale, a big assumption. In this case, essentially, we cannot explain the behavior of the galaxies. We cannot explain why in some places where we don't see very much matter, there is lensing, there is so the light is not propagated through a straight line, but it is bent, like there is some mass in there. So a number of things like that. And we call it dark matter. Then we have a good explanation for dark matter, a good hypothesis for dark matter in particle physics, in accelerators, by saying that, supersymmetric particles. Supersymmetric particles are particles which are sort of mirror-like to all the matter that we know and that we are made of. Pretty much in the same way as antimatter, but using a different type of symmetry. Instead of using the symmetry in this case of charge, and they're using another symmetry which is of the intrinsic angular momentum. And in this case, it would be very nice if this particle exists for 2 reasons. First of all, because they could unify, in our vision, matter, particle, and forces. And second, because they could explain dark matter. But in order just to do that, we have just to see, first of all, if they have the right characteristic. They should be heavy enough, there should be enough of them, stable enough, and then they should also behave in such a way that, for instance, if they are in the space, from time to time they annihilate, and by annihilating, they annihilating pairs of electron and positron. And since electrons are made many ways, it will be very difficult just to see, but positron are not so abundant. And if we measure an excess of positron in a certain energy range, then we know that they could be a very good candidate. So you see, it's the same measurement done in 2 different places, on the particle accelerator and on the space, which are all coming there. Of course, there could be even other explanation. We might discover, just putting the 2 things together, that supersymmetry does not exist, and that, for instance, gravity is not working the same way at all distances, and maybe that not all the dimensions in which we are describing the space are the right one just to describe. So it's open up a nice way of looking at things.
I think for tonight we'll stay in the dimensions that we're familiar with so far, and maybe save extra dimensions for another day. We next have a little clip about dark matter.
The universe around us seems to be made up of much more than what we can see. Indeed, the visible mass appears to be only a small fraction of the estimated total mass in the universe, and the observed motion of this visible mass suggests that it is mere flotsam on an invisible sea of unknown material. Galaxies are observed to rotate much faster than the visible matter in them requires them to. It would seem that invisible matter is stopping them flying apart. One explanation being postulated is that we are wrong to assume that gravity is unchanging and consistent over vast distances. Perhaps our current theory of gravity needs modifying. Another explanation could be that associated with each galaxy is an invisible halo of so-called dark matter, and it's this that's responsible for the galaxy's fast rotation. Looking for this dark matter will be CERN's Large Hadron Collider in Geneva, which will be on the hunt for an entirely new type of particle.
So we're flotsam floating on a sea of invisible matter. Michael, isn't that a little bit depressing?
Not so much depressing as humbling. I think it puts humanity in their place. But I find it actually more amazing or surprising that we can now start to address questions or experimentally give answers to questions that 2 or 3 generations ago people could not even formulate. We're now at a level of understanding the universe, or being able to understand the universe, that is far beyond what we've been able to do in the past. And experiments like this one here, like LHC, allow us to take the next step and answer these questions as well.
Indeed, you're absolutely right. Depressing is the wrong word. Humbling, more appropriate, and also actually rather enriching, perhaps, to think that we can even begin to comprehend these things. There's a lot of fascinating science, then, to be done with AMS, and we've only begun to scratch the surface tonight. But there's still a lot to do once the detector gets up to the space station before the data can start to flow. With Sylvie, can you tell us now comment us through this next clip. Tell us what happens when AMS gets up there.
So the next important milestone is the deployment of AMS from the shuttle to the ISS. And so I can comment. So 2 astronauts will be on the shuttle and will first unlock AMS system and then operate the shuttle robotic arm to transfer AMS to the ISS. 2 other astronauts from the ISS will operate the robotic Canadian arm in order to install AMS on the final deployment position on the S3 truss on the ISS. And then after that, they will release the robotic arm. Finally, the 2 astronauts on the ISS will make a tour around the AMS in order to check that everything is fine, and they will plug in the power and data cables. And then we can, as soon as the detector is ready, switch on the detector.
So after 10 years of working on this, you now have to entrust it to astronauts. Did you get a chance to meet them?
Yes, I was lucky. I met them in October 2009 when they came here at CERN, and they were very excited to come here and visit the LHC, but also they were really impressed by AMS and all the science surrounding linked to the AMS. So I was really impressed by their motivation. They are deeply involved in the mission. They have always good questions. They can concentrate on the point and anticipate also all the eventual problems. And they have a kind of self-control, which I was really impressed by them, but they are still modest and humble. and open mind. They ask a lot of questions about physics in general and also LHC. In particular, Mark Kelly was very interested by the LHC and the Higgs hunting. So it was really a good moment to share with them.
Mm-hmm. So you think AMS is in good hands?
Yes, I'm confident. I trust them. They also, of course, they know by heart what they have to do. They were trained in the pool, so they know how to cable this operation of the cabling or the transfer of AMS from the shuttle to ISS. They repeat a lot of time, and yes, I'm completely confident in this dream crew.
Dream crew there. Now, as well as being a scientific and a technological exploit, AMS is also a great human adventure. Let's hear from the deputy spokesman of the collaboration about that aspect.
AMS is an example of a very inspirational experiment for the young generation. The people which have worked with us in these many years have learned about science, physics, of course. They are motivated by the curiosity of making fundamental discoveries, but they also learned a wealth of knowledge how to design detector for space, how to operate with NASA, how to test this in extreme conditions, and so on. And they have been exposed to fantastic facilities at CERN, in Holland, by ESA, in Hestec, in NASA. They've been interfaced with many different culture, mentalities, organizations, and all of that in an experiment which is relatively small by the scale of today, very large experiment. We are probably altogether 500 people, but the core of the people which have worked together for these many years is probably about 100, 150, which is a small scale with respect to today's experiment. So I think this has been a very positive aspect of learning so many things and to live a so exciting experience in a context which was relatively human scale.
Roberto Battiston there telling us about the AMS collaboration. Sylvie, what's it like to work in such a team?
It was really different compared to the previous experiment where I was involved, because by definition AMS is a nomad experiment. We were obliged to test it in many different places, and so we have traveled all together to share this adventure and perform this measurement, this test. So it was really a great experience, human experience, yes.
So bringing people together makes it enriching for all of them.
Yes.
Arno, let's take one last dip into Twitter.
Oh, the last one. So perhaps you said the big word, Sylvie, and it will be more a question for Sergio. Sergio, we have many questions about the Higgs boson and the rumor we heard about in the last days, and people want to know if we have it or not.
I suspect it's a bit too early just to have it. But I would like just to tell people that we will not be waiting for a long time, in the sense that considering how the machine is working and the amount of data that the experiments are taking, it's very likely that within the year, or the maximum within the next 1.5 years, we will either have discovered the Higgs or have stated the fact that it's not there. We have just to find another explanation for the origin of mass. So it's exciting times. But I suspect that the rumors that have been spread out during this Eastern time were Easter rabbit.
Easter rabbits, but nevertheless an interesting promise there from CERN's research director. We won't have long to wait. Our final clip tonight comes from Maurice Bourquin from the Swiss team on AMS, and also a former president of CERN Council. He's going to tell us why endeavours such as the alpha magnetic spectrometer are also drivers of innovation.
Much of the resources that are needed for AMS to put such an experiment in space, in fact, are to use infrastructures that are working on the ground, but are not working yet in space. And we know for sure that space activities will develop. in order to understand better our environment. And for this, one has to develop new technologies. So much of the work which is done as a pioneer experiment with AMS will be used, I'm quite sure, to develop new ways to understand our Earth environment.
Shortly we're going to be going over to Florida, where we're going to be talking to my colleague Paola Catapano to bring us up to date. But before that, we've got a little bit more time, a few minutes, to talk about what's happening out on Twitter there.
Okay, so perhaps a question either for Michael or Sylvie. Some people ask if dark matter or antimatter could have a different effect on space-time than normal matter.
We're both trying to field the question and let the other one answer it. There's no obvious effect. One of the premises that we have in physics is that antimatter and matter have the same physical properties. So there should not be any effect on space-time. And also, dark matter is being postulated to patch an observational lack in a way. And it sort of postulates right there that it does not have any different effect than normal matter on space-time.
Okay. Yet your experiment is looking at the effect of gravity on antimatter.
Now, that is, of course, an open question, whether antimatter has the same gravitational interaction with matter as matter has with matter. And we'll see in a few years' time whether that is the case. But also there, that would not be a change in the space-time properties. It would just be a change in the description of gravity itself.
Which actually ties into something that Sergio was talking about earlier. Now, when we were talking about dark matter and dark energy and the fact that we're just 4%, ordinary matter seems to be just 4%, you gave us a hint that there might be another explanation for these phenomena.
Well, there could be large extra dimension, and then in this case, for instance, gravity would be modified by this, the existence of this large extra dimension if you are at that scale. And it will essentially, instead of going with the low 1 over the square of the distance, will go much faster than that, because we go like a power, which is connected to the number of dimensions. And this would change very much how the structure of the universe is done at different scales. The other thing is that if these extra dimensions are big enough that we can look at them with the microscope, which is the LHC, then in this case we can open them up for a small time, and we can either throw inside this extra dimension something or pull something out with spectacular effects, because, for instance, in this case, you don't have conservation of energy. And that would be a fantastic way in which you can prove things like that. Imagine that you are opening up a thing and it appears, a high-energy photon, not even coming from the place where you are making the interaction. It would be a totally mind-boggling thing. At the beginning, we might run even into the risk just to throw it away as a background. We have just to be very careful when we are selecting things. But this might open up a totally different way of looking at that. I mean, if at the time in which the universe was very hot, nature was living on many more dimensions, as for instance string theory requests, then it's not say that when it started freezing down, universe picked up the same 4 dimension every place.
This is really quite revolutionary stuff. I mean, I remember just about back at school that the first thing you learn is energy is always conserved, and there you've just thrown away a fundamental tenet of physics. So you're really ripping up the textbooks if this is the case. Arno, one more perhaps.
One more. A hard one again. Can AMS solve the wave-particle duality?
I'll try to answer that. Yeah. The wave-particle duality has to do with quantum mechanics, and quantum mechanics is something that is very well understood, very well tested, very much under control in the lab on the level of individual atoms. It can be manipulated with lasers. You can do a lot of work at that level. Now, at the level of the experiment AMS, there's no obvious link between the wave-particle duality or atomic physics and the processes that happen in outer space. Though there the processes are much more high-energy particles, or the characterization of specific particles. So I don't see an obvious link to that question.
Thank you.
Okay, we're just waiting now to get the live feed from Florida to talk to Paula, who's going to bring us up to date with the latest news. We're not quite there. So we've maybe got time for one more question.
Okay, perhaps it could be a good one for the last question. What could be the biggest possible success for AMS in 2030?
2030. Antimatter and dark matter and strangelet, everything, new particles, open new fields, new particle fields, new physics fields.
Okay, so it's time now. We're ready. We've got the feed from Florida, so let's go over to Paola, who's going to bring us up to date. Paola, what's the latest news from the Kennedy Space Center?
Bertolucci, la Sylvie Rosier e James Arnaud.
Ok, perfetto. Ma noi salutiamo perché non...
No, perché non comunichiamo con loro.
Apparently we still have a technical problem there. Let's take one more question on it.
Okay, so why is the AMS launch so unique?
By definition, from my point of view, every shuttle launch is unique because every time it's a different shuttle, it's a different event. But it's unique for us, of course, because AMS is in this shuttle. And it's unique because it's the first time we can launch so big detector, so huge detector, massive detector in space to take data during 20 years. So this is for one of the reasons for me why it is unique. It's a first attempt. It's an endeavor.
I'm just hearing that we can go back to Florida for Paola. Hello, Paola.
Hello, CERN from the Kennedy Space Center, Cape Canaveral. I'm here with Roberto Battiston, Deputy Spokesperson of the AMS experiment that is sitting in the payload of the Space Shuttle Endeavour. Right between us, you can see the world's most famous clock, the countdown clock of the Kennedy Space Center for the Space Shuttle launches. And unfortunately, it's counting up. This is the latest. The stopwatch is stopped counting down because, as you know, around 4 hours ago, there has been a scrub due to a failure to the power supply system of the Space Shuttle. Roberto can tell us more about it.
This is one of the systems which allow the shuttle to be powered before it's launched. And also is important during the flight phases to allow for some electricity to be available typically as a continuity type of support, a support system. The shuttle must fly with those units operational. The fact that the one unit gave some indication of malfunctioning had to stop the counting down. They have to fix that. Accessing those units unfortunately require removing the cold oxygen and hydrogen from the tank, so detanking, and then accessing this part, checking the performance, and maybe replace it. So for this reason, they calculated at least 72 hours of delay. There is a possibility there will be maybe 1 day more. At this moment, we're waiting for NASA to tell us exactly the situation. Any moment, they can tell us more precise information about that.
And indeed, there was a press conference planned for 4 p.m., but apparently they are still looking into the problem. They're still going on with the troubleshooting, and they postponed the press conference. They don't know when it's going to happen. They tell us, just wait and see. Roberto, what are your feelings right now? You were ready for launch. It's like a baby that has not been born yet.
Yeah, you know, we were really very optimistic about the launch today. Everything was aligning in that direction. The astronauts were passing nearby us just at the moment in the bus, in the famous bus, just at the moment this has been announced, and we saw the bus making a U-turn and go back. So really very deceived.
Yes, I saw that too, and you could see also on their faces. But in the meantime, President Obama has just landed on the premises right a few moments ago, and is at the moment visiting Atlantis. Any chance, Roberto, that you and the AMS collaboration are going to see him?
I have some doubt about it, but we are really proud that the President came here to see the launch of the STS-134, even if unfortunately the shuttle is still on the launch pad. It demonstrates how much importance the President and his staff give to this event.
Yes, so the launch is not today, it's probably going to be on Monday. Can you tell us, Roberto, what is going to happen to AMS once the Endeavour has lifted off?
Yeah, of course. In the first 8 minutes, of course, the Endeavour will go through the atmosphere at increasing speed until it reaches orbital velocity. At that moment, a few minutes after is out of the atmosphere, meaning 10 or 15 minutes after it's been launched, we will switch on the power supply of the AMS to ensure that the thermal systems are operational, because the shuttle will take about 3 to 4 days to orbit closer and closer to match the orbit of the space station and to reach the space station before docking. During this period of time, the temperature of the AMS has to be guaranteed within the range of survivability by a system of thermal control, which we have, a sophisticated one we have on board. For that we need the power, and that will be provided by the shuttle for this period of 3 to 4 days.
Okay, but you will have a signal from the AMS, your first signal that it has survived the liftoff. When is it going to arrive? For this, to see the first particle, we have to wait until the AMS is installed on the S3 main thrust side, on the location on the thrust side where we'll be operating for the next 10 or 18 years. And this will happen on the 4th day. On the 4th day, the astronaut will take the AMS out of the shuttle, transfer to the robotic arm which is on the space station, install on the space station, and then within maybe an hour or two, the experiment will be on, and at that moment we will get the first data down, and within minutes we will see the first track. Hopefully everything will go in this way I just said. And let's really hope that everything will go fine. Okay, one more question before this live link is over. Where are you going to follow the launch from? It depends when, of course. We still hope we can be still in Kennedy Space Center when the launch is taking place, otherwise in Houston, or if it is delayed too much, maybe even somewhere else. But we don't know yet. We hope we can see it from here. And we have to live with this unknown, unfortunately, but this is life. This is what big science and complex science is all about. Bye-bye CERN for now, and I'll keep watching Endeavour and what it's doing. I'll keep updating you through Twitter and maybe another webcast soon. Thank you very much, and bye everybody.
Thank you, Paola. And that just about brings things to a close for us too here at CERN. Thanks to my guests, thanks to you all for staying with us. I hope you've enjoyed it as much as I have, and I hope you'll join us again in a few days' time when they next attempt to launch Endeavour and the shuttle. Until then, we're going to leave you with some highlights of the AMS story to date. Good night.
Plus, we've done all the
There's JSC or here that can make that.
Yeah.
So be careful. Yeah. This is the high gain. You can see it's protected. So worst case,
This is sensor 2. This is sensor back.
You don't have any. You guys don't have any intention of get a prize.
Okay. 2 hours before launch, so 2 days before launch, you unlock
So it's fell down about 4 balls. Come up there right here, you see the shuttle itself, you see the vector. Right?
I am actually very calm. I'm confident everything will be okay because we did so much tests at CERN in the accelerators, and we tested detector twice in the accelerators and test in the thermal vacuum chamber in ESA. And we have taken the detector apart, assemble 3 times. So I think everything will work.
Oh, it's a very exciting time.
Where is the universe made out of antimatter?
We are looking for unusual phenomena.
And we call it astroparticle physics.
We're really excited about this upcoming mission.